I hope you enjoy this hero's journey into the realm of philosophy, psychology, and physics. If you want to help me create more content like this, please subscribe and consider sponsoring me here on YouTube. I also want to thank the Platonic Mystery School of the Divine Infinite Being for sponsoring this course, and you can check that school out at divineinfinitebeing.com.
Sir Isaac Newton, Mechanistic Cosmology. Newton, 1642 to 1727. So Newton's equations predict with godlike precision the positions and velocities of objects in our everyday experience of the world, based on the assumption that the cosmos is made of little bits of matter that endure, whether anyone is observing them or not, in 3 dimensions of rigid space, along a one-dimensional timeline that flows forward at the same rate for all observers, regardless of their relative positions or velocities. So this is the mechanistic cosmology of Sir Isaac Newton. Mechanistic, machine-like. Newton believed that there are 3 dimensions of space: up, down, left, right, backward, and forward. And they're rigid. They don't bend. They're not elastic like Einstein will later tell us in 1915. And he also believed in little tiny bits of matter, little atoms, that endure in space, and endurance is the passage of time. They endure through a linear, one-dimensional time dimension that flows forward at the same rate for all atoms, regardless of the relative velocities and positions of the observers. All this is going to change in the 20th century. But to understand the materialistic philosophy that Leonard Susskind himself still subscribes to, despite his knowledge of 20th century physics, we have to see how it starts here, really, with Isaac Newton's definitions of the cosmos. Little bits of insentient matter enduring through 3 rigid dimensions of space. Philosophia Naturalis Principia Mathematica, 1687. So here are Isaac Newton's definitions of space and time. Absolute true and mathematical time, of itself and from its own nature, flows equably without relation to anything external, and by another name is called duration. Absolute space in its own nature, without relation to anything external, remains always similar and immovable. So this idea of the 3 rigid, immovable, fixed dimensions of space, just empty space, and then this one-dimensional timeline where things just endure at the same rate everywhere, that is the framework within which Newton developed his laws of physics. So Newton's 3 laws of motion. Now, it's not so important to understand psyche equals singularity to understand Newton's laws of motion, but historically it's worth just going over the basic idea that people had in mind up until Einstein and special relativity in 1905. From 1687 to 1905, these were the laws of physics that reigned supreme. So every body continues in its own state of rest or of uniform motion in a straight line unless it is compelled to change that state by forces impressed upon it. So the 3 laws of motion, the first one is the law of inertia. The change of motion of an object is proportional to the force impressed and is made in the direction of the straight line in which the force is impressed. Number 2, the law of momentum, which is force equals mass times acceleration. To every action, there's always opposed and equal reaction. So other people say for every action, there's an equal and opposite reaction. Those are the first 2, and now the law of gravity is the third. The inverse square law, the gravitational force, the third law of motion. The gravitational attraction force between 2 point masses is directly proportional to the product of their masses and inversely proportional to the square of their separation distance. So the farther away the masses get from each other, the weaker the force of gravity gets. And as I said, understanding Newton's equations is not crucial for understanding the philosophical implications of psyche equals singularity, but historically it's important to know how the world was seen as a machine made of soulless little bits of matter, and it was within that framework that the idea of eternal souls performing their cosmic heroics for a supreme God living out at the horizon of the cosmos seemed primitive and superstitious, but how the same history of physics came full circle back to precisely that Platonic Vedic worldview. Spooky action at a distance. Newton's third letter to Richard Bentley, 1692. That one body may act upon another at a distance through a vacuum without the mediation of anything else, by and through which their action and force may be conveyed from one another, is to me so great an absurdity that I believe no man who has in philosophic matters the competent faculty of thinking could ever fall into it. Newton was suspicious of the infinitely fast force of gravity his own theory predicted. So according to Newton, and he realized this was a suspicious part of his theory of gravity, the gravitational force travels infinitely fast. It's an instantaneous connection between two massive objects. And that he called, later will be called spooky action at a distance, because it's implied also for quantum physics, that when you spin one quantum particle that was ever in contact with another, then no matter how apart they're separated in space later, if you twist one way, the other one twists instantaneously the other way, although the idea of twisting isn't the same as we perceive it in three-dimensional space when you apply it to quantum mechanics. But the point is, according to Newton, force of gravity travels infinitely fast, and that is what Einstein would later pick up on, and he saw how that contradicted the later discovery of the absolute speed of light, which led to special relativity. Newtonian dark stars, the first theories of a black hole. English cleric John Michell, 1784, and French mathematician Pierre-Simon de Laplace, 1796. Citing Newton's theory, both theorized stars so dense that not even light could escape their gravitational pull. So even using Newtonian physics and Newton's theory of gravity, the idea of stars that are so dense and therefore have such a strong gravitational pull that even light couldn't escape was there. That's a black hole. Now, Newton's theory doesn't imply that after a certain critical ratio of mass to radius, that star would collapse all the way down to a point of infinite density. That is general relativity. But the idea that objects might be so massive that even light couldn't escape from their gravitational pull, it's there even in Newton's theory of gravity. And that obviously is important to this class, where we are equating the psyche with the gravitational singularity at the center of a black hole. The speed of light, the first measurement. In 1862, the French physicist Léon Foucault, using an ingenious experiment involving a rapidly rotating mirror reflecting light off of a more distant mirror, measured the speed of light to be 299,796 kilometers per second, just 4 kilometers per second faster than the current measurement of 299,792, which is equivalent to 186,282 miles per second, or about 670 million miles per hour. So you can see that experiment in the image to the left. I'm not going to get into the details and explain it here, but it is an ingenious thing that as long ago as 1862, they were able to measure the speed of light. So 1862, the first measurement of the speed of light. Electromagnetic force. James Clerk Maxwell. In the mid-1860s, the Scotsman James Clerk Maxwell discovered that electricity and magnetism are one electromagnetic force. Oscillating electric and magnetic waves travel at the same speed as light, 186,282 miles per second, because the electromagnetic force is light. So he discovered, first, electricity and magnetism are one electromagnetic force, which travels at the speed of light because it is light. Absolute speed of light. Michelson-Morley experiment. Maxwell's equations provide no reference frame for the speed of light. Here's a quote from Brian Greene, string theorist. It was as if someone gave the location for a party as 22 miles north without specifying the reference location. Without specifying north of what? Brian Greene, The Fabric of the Cosmos. In 1887, Americans Albert Michelson and Edward Morley measured light traveling at exactly the same speed of 186,282 miles per second, regardless of the relative motions of the light source or its detectors. So the mechanism they used is up there on the upper left side of the screen. So this is the absolute speed of light. No matter how fast or slow you're moving in relation to the source of light, that your measurement will always come out the same. If you have two cars, they're traveling next to each other, and one is going 100 miles per hour and one's going 50 miles per hour. If the one going 50 miles per hour had a radar gun and shot it at the car going 100 miles per hour, that car moving at 50 miles per hour would detect that other car moving at just 50 miles per hour, because they're moving at half the speed of that other car. But if you were traveling at half the speed of light and you were measuring a light beam traveling at the speed of light, and you shot some kind of a mechanism that could detect the speed of light, it wouldn't measure half the speed of light to you, even though you are moving at half the speed of light. It would still measure that beam of light traveling at the absolute speed of light. That's very strange. It has enormous philosophical implications, as we will see. Albert Einstein, special relativity. In 1905, Albert Einstein reasoned that if velocity equals the distance traveled divided by the time spent traveling, that's v equals d divided by t, and if the velocity of light is always measured to be the same, then distance, or space, and time must be malleable. The absolute speed of light made Einstein reject Newton's concept of the absolute nature of space and time. So if you're measuring a light beam, and no matter how fast or slow, how quickly or slowly you are moving relative to that light beam, you will always measure it at exactly the same speed. Well, if the speed of light is absolute, then the nature of space and time must not be absolute. They must bend and twist in just the right proportion to the speed of light to keep it constant. As I will explain the next few slides, this gives rise to the notion of the elasticity of the fabric of space-time. And that was a huge departure from Isaac Newton's theory of the three rigid dimensions of space and the one unchanging, unmalleable linear dimension of time. Special relativity, length contraction, and time dilation. Light is always measured to be moving at the exact same speed because, this is what Einstein figured out, the length of each observer's measuring rod contracts in the direction of acceleration, and each observer's clock slows down with the increase in speed in just the right proportion that the measuring rods and clocks of all observers always measure the same light wave as moving at exactly the same absolute speed, regardless of their relative positions or velocities through space. So if you're in this car, to use the same analogy, moving at half the speed of light, and you're measuring a light beam that's traveling in a parallel to you, the reason that you won't measure that light beam traveling at half the speed of light, even though you yourself are traveling at half the speed of light, is because the measuring rod, whatever beam that you're using to measure the distance to the light beam, will be contracted in the direction of your travel. So if you have a yardstick, it's going to shrink down. If you have a foot-long ruler, 12 inches, then if the light beam travels 10 feet away from you in the split second that you do the measurement, each of your feet is going to have less inches in it because the entire ruler is contracted in the direction of travel. And furthermore, the clock that you're using to measure how long it takes that light to move will be slowing down. So that no matter how quickly or slowly you're moving, your rulers and clocks that you would use to measure a light beam's speed will be contracting and expanding depending on which direction you're traveling in such a way that no matter how you're traveling, no matter which direction you're facing, everybody will measure the same light beam as traveling at exactly the same absolute unchanging speed of light. Special relativity trains, clocks, and light speed. According to special relativity, if you could see a clock on a train as it speeds away from the platform at close to the speed of light, you would see the second hand moving very slowly, and the train itself would seem to contract dramatically in the direction of travel. But if you were on the train, you would see your clock moving at normal speed, while clocks on the platform would appear to be moving very slowly, and the platform itself would appear to be contracted in the direction of its apparent travel away from the train. This is the Jnana Yoga aspect of the class where you might start to feel your mind feeling the strain as if you were bending your body into a particular asana or yogic position. I'm feeling it myself every time I go over these concepts. It's like, okay, let me bend my mind into these shapes to understand the nature of the cosmos in which I live. As we go through these slides, the main point to keep in mind is that the implication of all these physics is that psyche equals singularity, and that the singularity is a point of infinite density in which the entire past, present, and future of the entire universe is condensed. And the reason that that should seem plausible is that it follows this trajectory of the history of physics, which we're going over now. Special relativity, relativity of simultaneity. Einstein imagined that from the midpoint of a railway platform, observers see themselves aligned with the midpoint of a passing train as lightning strikes the tracks at both of its ends simultaneously. From the midpoint of the train, passengers see the front lightning strike first because they are moving toward it, while they see the rear lightning strike after because it has to travel farther to get to their eyes. But if the movement of time is relative, so are the concepts of past, present, and future. In the next slide, we're going to see Brian Greene explain this in his own words, which will help to clarify. But if you look at the image, you can get an idea of the implications here. So you're standing in the midpoint of a railway platform and a train is passing by. Passengers at the midpoint of that train would see, from your perspective, you see lightning strike the front and the back simultaneously. But they will see the strike in the front first because they're traveling towards it, and that light from the back will have to travel to get to them. And the speed of light is not infinite, it's finite. Although it is absolute, and everyone will always measure the same light beam traveling at exactly the same speed, no matter how fast, how quickly or slowly they're moving, in relation to that light beam, it's still not an infinitely fast electromagnetic force. Okay, so from your perspective, the lightning hits the front and the back of the train simultaneously in the present. From the person on the train's perspective, the light from the front comes first and then the light from the back. So their concept of past, present, and future is different than yours. And the question is, well, who's correct? And Einstein will say both are correct from their relative positions, but the overall implication is that the past, the present, and the future coexist. Special relativity. Time is a persistent illusion. So that's a quote from Einstein that we will see. So here's a quote from Brian Greene. Once we know that your now can be what I consider the past, or your now can be what I consider the future, and your now is every bit as valid as my now, then we learn that the past must be real, the future must be real. They could be your now. With this bold insight, Einstein shattered one of the most basic concepts of how we experience time. The distinction between past, present, and future, he once said, is only an illusion, however persistent. So that's a quote from Brian Greene on the television show Nova, the series The Fabric of the Cosmos, The Illusion of Time. This is enormously important for an understanding of the self in relation to the cosmos. The past, the present, and the future coexist. Space and time are interwoven into a space-time fabric in Einstein's worldview. That fabric is elastic, according to general relativity, which is coming next. But even in 1905, with special relativity, Einstein discovered that just like in front of you in space is there, even though you are where you are, and behind you in space is there, even though you are where you are, similarly, the future in time is there, even though you're in the present, and what you perceive to be the past. It's not gone. It is also there. That's enormously important. Most people think, oh, the past is gone. You'll never get it back. It's nothing. It's just a memory now. And the future does not yet exist. But Einstein said, no, the future exists. The past exists. They could be the present, depending on which direction you're traveling and how swiftly. It cannot be underestimated how important it is to understand this. And it is always surprising to me how few people know this most basic fact of the history of physics. Einstein versus Darwin. No evolution if each point in the timeline coexists. So here's a quote from Einstein. It's in his book, Relativity. Since there exists in this four-dimensional structure, space-time, no longer any sections which represent now objectively, the concepts of happening and becoming are indeed not completely suspended, but yet complicated. It appears therefore more natural to think of physical reality as a four-dimensional existence instead of, as hitherto, the evolution of a three-dimensional existence. And then Sir Roger Penrose, who helped develop black hole theory and the theory of the Big Bang, especially in 1965, along with Stephen Hawking, Roger Penrose was the one who proved that a star of sufficient mass must necessarily collapse into a singularity when it burns through its fuel. So here's what Roger Penrose has to say. The idea that the history of the universe should be viewed physically as a four-dimensional space-time rather than as a three-dimensional space evolving with time is indeed fundamental to modern physics. So I have the title of this slide, Einstein versus Darwin, Because if we're trying to see ourselves as eternal souls performing cosmic heroics for God, then you have to confront the predominant paradigm of the self today, which is Darwin's theory that life evolved from matter and through the process of random mutation and natural selection resulted ultimately in human beings, and that self-awareness is a material byproduct of this material process of evolution. Well, whether the fossil record accurately indicates a development of one species into another or not, the entire paradigm becomes very problematic, the evolutionary paradigm, when you factor in special relativity, which says that the past, the present, and the future coexist. How can you have an evolution from point A to point Z on the evolutionary timeline if all of the points in between coexist simultaneously? That the point of questioning Darwin's paradigm is to help open space for you to perceive yourself as one with the gravitational singularity. All souls are rooted in this point of infinite density, which contains all space-time and radiates all space-time from the central point of the spherical universe outward and also inward from the spherical horizon of the cosmos. And when you realize the past, the present, and the future coexist, that's the first step in overcoming the materialistic concept of human consciousness as a bodily byproduct. E equals mc squared. The faster you go, the heavier you get. So this is an explanation that Einstein had for why nothing can travel faster than light. And that claim becomes very problematic inside a black hole, which is why Einstein rejected the theory of black holes to his death. Einstein realized that energy and mass are equivalent terms described with different units of measurement. To translate units of energy into units of mass, Einstein multiplied the units of mass by the speed of light squared. E equals mc squared. Energy equals mass multiplied by the speed of light squared. No massive object can travel at the absolute speed of an inherently massless photon because the faster massive things travel through space, the more kinetic energy they accumulate, which gives them more mass. You would require an infinite amount of energy to accelerate a massive object to light speed, which Einstein thought is impossible. So the faster you move, the heavier you get. As we'll see with general relativity, it's g-force. If you are in an automobile and you slam on the gas pedal, you feel yourself pressed against the seat. If you had a scale behind you, the scale would register that increase of weight. Well, the faster you go, the heavier you get. Therefore, you require more energy to accelerate you more swiftly. And as you approach the speed of light, the amount of energy you would need to make you go faster would approach infinity. That's why he said nothing can travel faster than light. And then when he discovered the implications of his own theory of gravity, that they imply black holes where space-time itself travels faster than light past the event horizon and infinitely swiftly at the central point, that's why he rejected the idea of black holes. E equals mc squared. Newtonian gravity breaks the speed limit of light. Einstein believed that nothing at all can travel faster than light. He realized, however, that according to Newton's theory, the force of gravity travels infinitely fast in that it acts instantaneously between distant objects. He therefore set about rendering the speed of the gravitational force consistent with the speed limit of the electromagnetic force, or light. And that will lead us to general relativity. General relativity, Einstein's theory of gravity. So this story is about Einstein's happiest thought. While he was working as a patent clerk in Bern, Switzerland in 1907, 2 years after he discovered special relativity and his equation E equals mc squared, he still wasn't world famous. He was still working as a patent clerk. But while sitting in his humble office in Bern, he looked out the window across the street and he had his happiest thought, which is that gravity and accelerated motion are equivalent. Einstein, watching workers on a roof, realized that if someone were to step off of a high building and drop a ball at the same time, the ball would remain right next to the falling person, as if the force of gravity in the person's local reference frame had been neutralized by the force of acceleration. Similarly, an elevator accelerating upward creates the same force as gravity pulling downward. So if you are holding a ball and you step up off of a roof and you let go of the ball, you and the ball will fall at the same rate and the ball will remain right next to you, as if in your little part of the universe, gravity had been turned off. So Einstein was looking for a way to harmonize the force of gravity with the absolute speed limit of light, upon which he based special relativity. Newton's theory of gravity indicates that the gravitational force travels infinitely fast between massive objects, something that Newton himself realized and knew that that was a big problem. So trying to solve this problem, Einstein had the happiest thought, in his own words, of his life when he imagined a worker falling off of a roof. That seems to be a dark thought, but it opened up a brilliant realization of the equivalence of accelerated motion and gravity. Now, as a preface to the history of philosophy from Plato up to Carl Jung, let me just say Immanuel Kant talked about the nature of space and time. He was responding to David Hume, who was an empiricist who said, if you can't perceive something with one of your 5 bodily sense organs, if you can't see it, smell it, touch it, taste it, or hear it, then it's just a figment of your imagination. And Hume himself pointed out, you can't see, smell, touch, taste, or hear space or time or causality, for that matter. Immanuel Kant said Hume had awoken him from his dogmatic slumber, and he came up with the theory that space and time are what he called a priori categories of thought, lenses of cognition, inborn psychological lenses through which your bodily sense perceptions are filtered to your mind. So space and time, according to Kant, are the mind. So that's just important to keep in mind as we're discussing the evolution of physics and the evolution of the understanding of space-time. As we'll be discussing later, space-time is the mind. So the elasticity of space-time, culminating with the gravitational singularity, where the curvature of space-time reaches an infinite degree inside a black hole, I'm saying that is the psyche. So that's just a preface that we'll be returning to. General relativity, gravity equals curvature of space-time. According to general relativity, the mass of the sun creates an indentation in the three-dimensional surface of the four-dimensional fabric of space-time in the same way that a bowling ball creates an indentation on the two-dimensional surface of a three-dimensional trampoline. The planets orbit the sun in the same way that billiard balls rolling across the surface of a trampoline revolve around the indentation created by a much more massive bowling ball. So we can't imagine, with our everyday consciousness that's used to living in a three-dimensional world, what a four-dimensional object would look like. So we use the dimensional analogy of a two-dimensional surface of a trampoline to represent the four-dimensional space-time, and how the surface of that four-dimensional space-time could be curved. That's something that it's impossible, at least for most human minds, to imagine. But most people have seen on television, on videos, the demonstration of taking a bowling ball, putting it on a trampoline. It creates this massive indentation in the center of the trampoline, and then you roll billiard balls straight forward across the trampoline, but they get caught into an orbit around the bowling ball because they're following the contours of the surface of the trampoline. And that's the same thing that happens as the planets are orbiting the sun. They're caught in the indentation in the fabric of space-time, and that's the force of gravity. It's not some infinitely fast tether between the sun and the planets like Newton's theory assumes, even though Newton himself was suspicious of this infinite speed of gravity, this instantaneous connection between two gravitational sources. So Einstein solved that conundrum with general relativity. General relativity, gravity and the vaporized sun. According to Newton's theory, if the sun vanished, the gravitational tether connecting it to the planets would too. They would instantaneously careen out of their orbits, indicating an infinite speed of gravity. According to general relativity, the outward rippling gravitational wave of the rebounding fabric of space-time would travel at the same speed as an electromagnetic wave. That's light speed. It would take about 8 minutes to reach Earth. Gravitational waves were first detected on September 14th, 2015. So, according to Einstein's theory, gravity travels infinitely fast, as if the two massive objects were in immediate contact. Their gravitational connection is instantaneous. Newton realized that it seems philosophically impossible for any force to travel infinitely fast. So according to Newton's theory, it's as if the planets are tied to the sun with a rope. And just like if you were holding a rope with an object tied to the end of it and you spun it around your head, if you let go of the rope, then that object, the other end of it, would shoot off into a straight line away from you at whatever angle it was that you let it go. So, to use a thought experiment, if you imagine the sun just vaporizing all of a sudden, according to Einstein's theory, the planets would just shoot out of their orbits instantaneously because that tether would be cut. It would be no longer. But according to Einstein's theory of gravity, the orbits of the planets are caused by the indentation in the fabric of space-time created by the sun. All of a sudden vaporize, that elastic fabric of space-time would bounce back up, and it would send a rippling wave through space-time that would travel at exactly the speed of light. The force of gravity is the same as the speed of light. It cannot go faster than light according to Einstein's special theory of relativity, and his theory of general relativity explained what gravity is. It is the curvature of the fabric of space-time. General relativity, a Trojan horse. So these quotes come from the famous string theorist Michio Kaku. So why did he call general relativity a Trojan horse? So according to the myth of the Trojan horse, the Greeks were trying to invade the city of Troy, and for 10 years they attempted unsuccessfully. So they finally came up with a strategy to construct an enormous hollowed-out wooden horse that they would offer to the people in Troy as a gift. But they would have soldiers hiding inside the wooden horse, and then when the horse was drawn inside the city, the soldiers would pour out of the horse and conquer the city, which they did. So why does Michio Kaku call general relativity a Trojan horse? What kind of deadly enemies are hiding inside general relativity? So here's his quote from his book, Hyperspace. Inside lurk all sorts of strange demons and goblins, which allow for the possibility of interstellar travel through wormholes and time travel. The price we had to pay for peering into the darkest secrets of the universe was the potential downfall of some of our most commonly held beliefs about our world, that its space is simply connected and its history is unalterable. So we'll be quoting from Michio Kaku a lot. I've learned a lot from him. I enjoy reading his books and watching the videos that he's presented out on YouTube and other places. But let me just state clearly that Michio Kaku, like Leonard Susskind and Brian Greene and other physicists from whom I've learned a lot and respect a lot, nevertheless, they are atheists. So when the implications of general relativity and quantum mechanics indicate something that resembles the idea of God, they become very suspicious, and it becomes this nightmarish scenario to them. When Michio Kaku talks about the darkest secrets of the universe, he's talking about black holes, from which not even light can escape, and the singularity inside black holes. That's the reason that general relativity is a Trojan horse. It gives us the idea of black holes where space-time is contracting toward the central singularity at an infinite speed, and it starts to give the same philosophical implications that come from theology and the idea of an omnipotent, omnipresent, omniscient, infinitely brilliant God. That is a dangerous thing for atheistic physicists because it seems to them like a regression to dark ages and ignorance and superstition. Carl Schwarzschild. First description of a black hole. On December 22nd, 1915, Carl Schwarzschild wrote a letter to Einstein that provided the first precise mathematical solution to the gravitational field equations of general relativity, which Einstein helped him publish in January 2016. So the precise solution to the gravitational field equations, I'm not a mathematician, I'm not a physicist. I studied philosophy, but I studied the philosophical implications of the evolution of physics. So I don't know what an exact field equation is versus Einstein's approximate field equation, but at any rate, on December 22nd, 1915, that's when general relativity was given its first precise description, and Einstein was very happy about that, and he helped Schwarzschild publish his article. However, a few weeks later, Schwarzschild sent a second paper, this time describing infinite spacetime curvature inside a star. It was the first description of a singularity inside a black hole. Einstein rejected the idea up to his death in 1955. So, in February 2016, Schwarzschild published a paper describing a star that was so massive that it collapsed into a point of infinite density, that the gravitational force, once it reaches a certain intensity, becomes infinite. It was so the few weeks after the first precise description of general relativity was given by this man, Carl Schwarzschild, he came up with the idea of black holes. And Einstein hated the idea. Not that Einstein was overt atheist and that he hated the idea of a singularity because he hated the idea of God. Einstein could be considered a deist, like the founding fathers of the United States of America. He believed in some kind of rational force that organizes the universe. It doesn't seem like he considered that force to be a personal God, even though he was Jewish, and the Jews definitely consider the omnipotent God to be a personality with whom you can develop a relationship. Einstein doesn't seem to have believed in that, but he did believe in some kind of rational ordering principle that pervades the universe. He even once famously said, to contradict the new theory of quantum mechanics, that God does not play dice. So the reason Einstein detested the idea of a black hole wasn't because it reminded him of the idea of God. It's because inside a black hole, the laws of physics break down completely. Space and time come to an end, and the equations that Einstein worked so hard to discover no longer make sense. So to his death, Einstein rejected the idea of black holes, which his own theory predicts. Cosmological constant, the original dark energy. Einstein, who believed the universe is static, meaning it doesn't move, realized that without anti-gravity to counteract the attractive force of all matter, the universe would be contracting. In 1917, he therefore inserted the cosmological constant, symbolized by the Greek letter lambda, a repulsive force of anti-gravity, into his general relativity equations. So he came up with this idea of a cosmological constant. It's this constant force of anti-gravity present in the universe that he just inserted into his equations to counteract the force of all matter for all other matter, which would be causing the universe to contract. His assumption is that the universe is static. It doesn't expand, it doesn't contract, it's just the same throughout all time, and the past, the present, and it contains the past, the present, and the future like a big block of ice or a big loaf of bread. So, to make sure the universe wouldn't contract in on itself, he inserted this idea of the cosmological constant. We're going to see in subsequent videos that idea of a cosmological constant has been reborn as the idea of dark energy, but that's just a preface to that. Birth of the Big Bang Theory. Georges Lemaitre. In 1927, Georges Lemaitre, a Jesuit priest from Belgium, was the first theorist to propose both the exponentially expanding space-time theory and the related theory that in the past the universe was contracted into a single point, which he called the primeval atom, the singularity of the Big Bang. Einstein told Lemaitre, "Your mathematics are correct, but your physics is abominable." So Georges Lemaitre, Jesuit priest, observing Einstein's equations for general relativity, discovered that they indicate that the universe, this fabric of space-time, is expanding. And if it's expanding, that means if you go back in the past, it was contracted. If you go back far enough, it was contracted into a single point. He called it the primeval atom. That's the singularity of the Big Bang. That was the birth of the Big Bang Theory. Einstein, who detested the idea of black holes because they contain singularities, also therefore detested the idea of the Big Bang from a singularity. The universe is expanding. Hubble constant. In 1929, Edwin Hubble used the 100-inch mirror in the largest telescope of his day at the Mount Wilson Observatory in Pasadena, California, to observe that what were then believed to be stellar nebulae are actually independent galaxies, and that those galaxies are accelerating away from Earth at an increasing rate proportionate to their distance, which is now called the Hubble constant. This indicates that the universe is expanding from a singularity. After Hubble's discovery, Einstein called his theory of the cosmological constant the biggest blunder of his life. However, as we will see, Einstein's cosmological constant has subsequently been reincarnated as the dark energy of the quantum vacuum. So Pasadena, California, Edwin Hubble, he's looking through this reflecting telescope, the largest one of his day, and what were previously considered to be stellar nebula, clouds of star dust out at the edges of the universe, they thought. He discovered that those aren't clouds of stardust in the universe, those are independent galaxies. That the universe is much more enormous than people had suspected, and that furthermore, each of those galaxies is expanding away from Earth at a rate that increases the farther away from Earth that they are. And that distance to speed ratio is called the Hubble constant. So a lot of people have seen the demonstration of gluing pennies to a balloon. We'll be discussing it later, but if you were to do that and then inflate the balloon, those pennies would expand each one away from the other. And the bigger the balloon got, the faster those pennies would be expanding away from each other. At any rate, the main point for this slide is that if the universe seems to be expanding, then in the past it must have been contracted. And so here was the empirical evidence in favor of a Lemaitre's theory of the Big Bang from a gravitational singularity. Einstein then went back and accepted Lemaitre's theory. He rejected his own theory of the cosmological constant, the anti-gravitational repulsive force, which he inserted into his equations in 1917 to counteract what he thought was the attractive force for all other matter, which should be causing the universe to contract. So he accepted the Big Bang theory, but even after that, he still rejected the idea of a gravitational singularity. The universe must have expanded from some extremely dense and energetic point, but it couldn't have been infinitely dense, according to Einstein's speculations.
I hope you are enjoying this hero's journey into the realm of philosophy, psychology, and physics. If you want to help me create more content like this, please subscribe and consider sponsoring me here on YouTube. You can also click the link to my website, psycheandsingularity.com, to sign up for a multiple-choice test with over 100 well-crafted questions related to this class, and links to the specific parts of each video where the answers can be found. If you take that test to the end, you will receive a certificate indicating that you have become a Psyche and Singularity scholar. In addition to access to that test, there is also the opportunity to answer essay questions that ask you to relate concepts covered in this class to your own hero's journey. I will personally respond to each of those essays, point out any other parts of this class that I think might bolster your plan. Finally, I want to point out that this course is sponsored by the Platonic Mystery School of the Divine Infinite Being, and you can check those guys out at divineinfinitebeing.com.